The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
The topic for today is going to be equations of planes. And how they relate to linear systems and matrices as we have seen during Tuesday's lecture. So let's start again with equations of planes. So remember, we've seen briefly that an equation for a plane is of the form ax plus by plus cz equals d, where a, b, c, and d are just numbers. Okay, and so this expresses the condition for a point at coordinates x, y, z to be in the plane. And so an equation of this form defines a plane. So let's see how that works again. So let's start with an example. Let's say that we want to find an equation for the plane through the origin with normal vector let's say vector n equals, let's say, the normal vector 1, 5, 10. Okay, so how do we find an equation of this plane? Well, remember that we can get that equation by thinking geometrically. So what's our thinking going to be? Well, so we have the x, y, z axes. And we have this vector n, 1, 5, 10, and it's supposed to be perpendicular to our plane, and our plane passes through the origin here. Okay? So we want to think of a plane that's perpendicular to this vector. Well, when is a point in that plane? Let's say we have a point P, at coordinates x, y, z. Well, the condition for P to be in the plane should be that we have a right angle here. Okay. So P is in the plane whenever OP dot n is 0. And if we write that explicitly, well, vector OP has components x, y, z, and has components 1, 5, 10. So that will give us x plus 5y plus 10z equals 0. Okay, that's the equation of our plane. Now, let's think about a slightly different problem. So let's do another problem. Let's try to find the equation of a plane through a point P0 with coordinates, say, 2, 1, minus 1, and with normal vector, again, the same guy, 1, 5, 10. Okay. So how do we find an equation of this thing? Well, we are going to use the same method. In fact, let's think first for a second. So I said we have our normal vector n, and it's going to be perpendicular to both planes at the same time. So in fact, our two planes will be parallel to each other. The difference is, well, before we had a plane that was perpendicular to n and passing through the origin. And now we have a new plane that's going to pass, well, not through the origin, but through maybe this point P0, and I don't really know where it is, but let's say, for example, that P0 is here. Then I will just have to shift my plane so that instead of passing through the origin, it passes through this new point. Okay? So how are we going to do that? Well, now, for a point P to be in our new plane, we need the vector no longer OP, but P0P to be perpendicular to n. Okay? So P is in this new plane if the vector P0P is perpendicular to n. And now let's think for a second, what's vector P0P? Well, we take the coordinates of P and we subtract those of P0. So that should be x minus 2, y minus 1, and z plus 1, dot product with 1, 5, 10 equals 0. Or let's expand this. Well, we get x minus 2 plus 5 times y minus 1 plus 10 times z plus 1 equals 0. Or let's put the constants on the other side. We get x plus 5y plus 10z equals, well, here we have minus 2 becomes 2, minus 5 becomes 5, 10 becomes minus 10. I think we end up with negative 3. So, see, the only thing that changes between these two equations is the constant term on the right-hand side, the thing that I call d. And the other common feature is that the coefficients of x, y, and z, 1, 5, and 10, correspond exactly to the normal vector. Okay, so that's something you should remember about planes. These coefficients here correspond exactly to a normal vector. And, well, this constant term here roughly measures how far, when you move from, so if you have a plane through the origin, the right-hand side will be 0. And if you move to a parallel plane, then this number will become something else. So how actually could we have found that minus 3 more quickly? Well, we know that the first part of the equation is like this. Okay? And we know something else. We know that the point P0 is in the plane. So if we plug the coordinates of P0 into this, well, x is 2 plus 5 times 1 plus 10 times minus 1, we get minus 3. So in fact, the number we should have here should be minus 3 so that P0 is a solution.